Welcome to ICDD's InSession webinars and Dr. Tom Blanton's presentation, Better Data Equals Better Results. Please remember to visit ICDD.com for information on free webinars, educational events, PDF databases, and JADE software.
All right, everybody. Hello again. Tom Blanton here from ICDD. Today's presentation will focus on powder diffraction, and in particular, some things to think about as you collect your data, prepare your samples, and how it will help you get better results, particularly for phase identification applications. I would like to note that some of the slides I'll be using have contributions from Cyrus Crowder, Tim Fawcett, Mark Rodriguez, and Scott Speakman. So I thank them for their contributions in what I'll be showing today. Topics to be covered include specimen transparency and displacement, counting statistics, step size, particle statistics, the effect of preferred orientation, and the effect of low sampling statistics, and how all of these affect your data in terms of being able to get good peak positions, peak intensities. A slight disclaimer, we'll be showing some images that may include equipment or components from different manufacturers. We are not saying this is an endorsement by ICDD. They are used for demonstration purpose. We like everybody, so you certainly can choose particular instruments that you like. We just have some shown here for demonstration purposes. Just as a quick reminder, we're interested in powder diffraction. When you look at a single crystal sample and you radiate with your X-ray beam, you get what we would refer to as Lowy spots. These spots are indicative of different diffractions from lattice planes. When you have your powder sample or polycrystalline sample, you have individual small crystallites, and you get a summation of diffraction from the different crystallites that the summation of these spots give you what we refer to as the Debye rings. And this is what we're really picking up when we look at a powder diffraction pattern from a diffractometer. And more specifically, you can think of your diffractometer as contributing essentially a small slice of the Debye ring, and if it's a random powder, no matter how you orient the sample, you would get the same pattern. If there's preferred orientation or large crystallites, you might see some differences, and we'll hit on this a little bit later in the presentation. So the focus here today will be on the Bragg-Brentano diffractometer, primarily in reflection mode geometry. And the diffraction pattern that you get is typically an intensity versus 2 theta plot. The 2 theta, the peak positions, tell you something about the unit cell parameters. 2 theta can be converted to d-spacing utilizing Bragg's law, and it's these positions, these d-spacings, that are related to the unit cell. The peak intensities tell you something about the atomic positions, where the intensity is proportional to the structure factor, which is related to the scattering, as well as the XYZ, the atomic position, for a specific lattice plane HKL. And the background tells you something about the crystalline amorphous content of the sample, and this is what we utilize for our phase identification. Now, the Bragg-Brentano diffractometer has different configurations. Today, probably the most common is the theta-theta geometry, where the sample remains flat, the X-ray source and the detector move together, and the detector moves at an angle 2 theta relative to the direct beam. So this is why your plot is I versus 2 theta. You can also have a geometry where the tube is set, the sample stage will move, the detector moves, or you can have a horizontal position where the source is fixed. Again, the sample moves, the detector moves, but in all cases, it's the detector relative 2 theta to the direct beam. Now, in the choice of your radiation, we commonly hear for powder XRD that the most common radiation is copper. Sometimes you will hear cobalt, you hear some other radiations. But if you compare molybdenum versus copper versus chrome, and we look at a particular diffraction pattern and focus on a specific diffraction peak, you can see that for molybdenum radiation, that peak shows up at a lower 2 theta. For chrome radiation, a much higher 2 theta, and copper radiation, the 2 theta is somewhere in between. The choice here, the moly, you tend to have a little less resolution. Chrome, you have much better resolution. And then copper is somewhere in between. But the problem with chrome is being a lower energy means that you have more attenuation of the chrome K-alpha X-ray just due to the air path that the X-ray beam travels in your diffractometer. So copper radiation is a good compromise between the resolution of your diffraction peaks as well as better issue around the air attenuation compared to chrome. Now, this is for laboratory sources. As you go to something like a synchrotron, the issue around resolution and the issue around intensity is pretty much a non-factor. So if you're using synchrotron, you may be using very short wavelengths, you may be using long wavelengths, all will work fine. But for the laboratory, you're more common to find copper K-alpha radiation instruments. Now, in the publication book from Jenkins and Snyder, they have a figure in there that talks about common diffractometer errors, and this is kind of where our focus is going to be today. And they talk about different errors that occur that will shift your diffraction peak positions, and it's these shifts that cause problems with phase identification. So we're going to focus on 2 of them today. One is called the displacement error, and one is transparency. So what do we mean by that? If you take your Bragg-Brentano diffractometer, there's an imaginary focusing circle where the source, the surface of the sample, and your receiving slit are on this focusing circle. If you have transparency or sample displacement, specimen displacement, what happens is you're no longer on the focusing circle and you're displaced by some amount. And this displacement is changing the radius around the sample, and that in turn is going to result in a shift in where the diffraction peak is observed as you're scanning through your detector on the instrument. And so this transparency and displacement effect are probably the 2 most significant effects you see in diffraction peak position shifting. So let's talk about specimen transparency. If you're looking at a material that's strongly absorbing of X-rays, you typically get your diffraction pattern just from the near surface of the sample. But if you have a weakly absorbing material, for example, organics related to your X-ray beam, you tend to penetrate much deeper into the sample, and therefore you're going to see what we would refer to as a shift and a broadening of the diffraction peak. There is an equation we can use to calculate this delta 2 theta, and it's related to the angle that you're collecting data, the radius of your diffractometer, and something that we call the linear absorption or linear attenuation coefficient. Now, this coefficient varies depending upon the radiation you're using, the elements of the phase that you're looking at, as well as the density. So as an example, if I'm working with a benchtop type diffractometer that tends to have a shorter radius, I'm looking at a peak at 44 degrees 2 theta. I'm using copper radiation. The attenuation, linear attenuation, which is a product of mass absorption coefficient times the density. We can see for iron, this number is rather large. For a polymer sample, such as polyethylene, the number is very small. So the shift in your peak position for iron is so small that in a powder diffractometer in your lab situation is negligible. You really won't see a peak shift due to transparency. But in a organic, like a polymer sample, you'll see the shift is rather large, almost 4/10 of a degree to theta. And this can affect your ability to identify phases if your peaks are shifting around. If you just look at a basic calculation, what you see if you're comparing carbamazepine, which is a pharmaceutical material, compared to aluminum oxide, you'll see that the delta to theta value is rather large for the carbamazepine. And you'll notice what happens is that this air increases till you get to about 90 degrees to theta. And then the air will decrease as you go to a higher angle. So what does that mean that you see? If I'm looking at an organic material and I'm trying to match the peaks to some reference, as I go, if I have a thick sample, as I go to higher and higher angle, I'm going to see my peaks consistently continue to shift to larger and larger 2 thetas. And so sometimes people will say, how come I'm seeing this effect? This is your transparency error. You're penetrating deeper into the sample. So what causes this? In most instruments, diffractometer instruments, the conventional sample holder that's provided is something that we call a front load cavity holder. It's cut out in typically a piece of plastic, a polycarbonate, for example, or aluminum, and you load the sample from the top and you pack it into your holder, okay? The problem is that when that's a thick sample, you're going to get good intensity, but if it's an organic or a low absorbing material, your X-ray beam penetrates deep into the sample. If you make a thin specimen where you have just a thin coating or a thin powder layer, you don't really have this penetration depth issue because you don't have a thick sample. So you're going to get better peak position determination, but your intensity is going to be low because you have less material that's diffracting. An example here would be using what we call a zero or low background holder, and we'll get into this in the next couple of slides. So what happens when I have the cavity, I pack it full of material, and if the Z is low, carbon, hydrogen, nitrogen type materials, I get deep penetration into the sample, and I have a shift of my diffraction peak to lower 2 theta. If I have a thin specimen and the specimen is just a thin coating, then I get the correct position, and therefore I don't see that shift. Here's a diffraction pattern of something we call a zero background holder. The zero background is a special cut on either single crystal silicon or quartz. The silicon is typically cut on the 510 lattice plane. So that's a forbidden reflection for silicon, and so you don't see a diffraction peak. For quartz, it's typically about 9 degrees off of the OOL axis. And again, if it's cut properly, you don't get diffraction peaks. You get very little background, and you would sprinkle a little bit of sample on top of your holder. Here's an example of a diffraction pattern of a silicon special cut, and you'll see that it's flat in the background, a little bit of direct beam and air scatter, flat background, and you don't get any contribution from that holder. So an example here's ibuprofen, a pharmaceutical, over-the-counter pharmaceutical, and we have 2 diffraction patterns here. One, the specimen that was packed in a front pack depression holder versus one sprinkled on a silicon background plate. And you'll see in this plot here, the absolute intensities, a little bit easier to see if you normalize the intensities. And the components that you see are that the thin specimen sample has better peak resolution, okay? but in the original plot, we saw its lower intensity. The pattern from the thick sample, the black pattern here, we see that the resolution is reduced because you're looking at now a thick specimen, and all the peaks have shifted to lower angle compared to where we saw it in the thin specimen. Now, if you knew that you were looking at ibuprofen, and you just wanted to say yes or no, you probably could at least manually identify the phase. But this shift is pretty significant, and if you use automated peak finding and automated phase ID, you might miss the phase if you don't have a large enough shift error in your diffraction searching. So where do you get these silicon or quartz plates? Again, this is just for information purposes. 3 sources. There's a group here, and you'll have this information available when the video is made online. This particular group, MTI, will sell the individual pieces that you can mount in your own holder. They sell both silicon as well as off-axis quartz. I will say the quartz is more durable. The silicon tends to be a bit fragile. They sell 1 and 2 millimeter thick silicon. The 1 millimeter can crack easy. The 2 millimeter is a little more durable, a little more expensive. One thing I will say about the silicon, the silicon dioxide, is sometimes, even though they do the off-axis cut, if you're using it in a sample holder in your instrument and you're using a sample spinner, occasionally a Lowy spot will show up and you'll get a very sharp spike in your diffraction pattern. The silicon tends to be a little bit cleaner in that case there. So durability versus the silicon a little cleaner sometimes. The key is if you order any of these pieces, run them as a blank in your instrument to make sure that they are in fact crystallographically and powder pattern clean. Other suppliers include KSA. They're based in the United States, and they will make holders specific for your instrument. Another group, Crystal Scientific in the UK, also will make holders specific for your instrument. So there are some sources that you can get these zero background plates. Plus, typically your instrument manufacturer can also supply them as well. Another advantage of using the silicon plates or the zero background holders is sometimes you have very small sample and you don't have enough to pack into your holder. So here's a case where we're presented with a rock mineral sample, and we were allowed to take 1 magenta particle out of it and then a little bit of sampling of the matrix around it there. You don't have enough to fill a sample holder, but you can crush the individual particle, mount it on a silicon background plate, and we get a beautiful pattern that it was a garnet, an almandine type garnet, and we get a perfect match for the phase in the powder diffraction file. If we take a look at one of the little matrix components, we were able to identify the major phases as quartz, albite, and there is a mica present, probably muscovite based on the color of the matrix there, but you could identify it with just a very minimal amount of sample. So another advantage of using these background plates. Now let's talk about the specimen displacement error. Again, the same kind of holder. And in this case, it's not so much what's the chemistry of the sample, but how well is it positioned in your sample holder. If you have the right amount of sample and the sample is level or basically at the plane of your sample holder, we say that you're in a zero displacement and you would see your peak showing up at the correct 2 theta. But if your sample or specimen is displaced low relative to the sample plane, this is very similar to your transparency issue. You'll see the peak shift to lower 2 theta. If you're displaced high, meaning you have too much sample in the sample holder and it's mounted above the sample plane, you will see your peak shift to a higher 2 theta. Sample or specimen displacement is probably the most common error that you'll see in your powder diffraction analysis. And high displacement is more common because people will pack the holder but not check to see what's its level relative to the sample plane. There is an equation similar but a little bit different than the transparency. And here we're looking at our displacement as a function of angle, in this case theta instead of 2 theta. You talk about the radius of the diffractometer, but you'll notice we don't have a linear attenuation coefficient here because this calculation is independent of the composition, strictly on the positioning of the sample, your displacement S. And again, here's a case where if you're at 12 degrees 2 theta, the radius, like a benchtop diffractometer, 150 millimeters, and if you had 100 micron specimen displacement. What's 100 microns? Not too dissimilar from the thickness of a human hair. You will shift about 0.08 degrees 2 theta in this particular case, okay? So you think about particles that you're working with, and maybe if it's a 200 micron, 300 micron particle, and you're just displaced one particle, you can have quite a shift in your 2 theta. If you show this graphically, what you'll see is, unlike the transparency error, which peaks at 90 degrees 2 theta, your displacement error peaks at 0 degrees. In other words, it's worse at low angle than it is at high angle. And depending upon the amount of displacement, will tell you the amount of delta 2 theta. An important thing here is that people might look at this and say, oh, well, great, I'll collect all of my data at high angle. That's what we would like to do. The problem is that your intensity tends to be very low at high angle because your scattering factor drops off as a function of 2 theta. Most of our diffraction data is taking place, say, below 80 degrees 2 theta, and for organics in particular, it tends to be below 40 degrees 2 theta, where you get most of your diffraction peaks using copper radiation. So the careful preparation of your sample here is important to reduce the delta 2 theta. So an example here, just something to consider, and every instrument's a little different, but as one example, here is a sample stage in a diffractometer. So the way it works is that the specimen is put in the stage and you push it up into position, and there are little pins and one hidden back here that the sample holder presses up against. And so it is that position that is in the correct, we'll call it the stage position of the sample. And now you want to know, where's my actual powder relative to that? So this is a holder that has a silicon background plate in it, but the plate is actually mounted just a little bit below the sample holder plane, so that when I sprinkle powder on it, it's nominally level with the plane, so I don't create a displacement error. Everybody's instrument is a little bit different, but typically there's some kind of reference point that you want your sample holder plane to be in position for correct alignment. Example of the effect, here is a coating of kaolin on glass, and when the sample is in the 0 displacement spot, we get our diffraction peak. If it is displaced high, you'll see that the peak shifted to higher 2 theta, and you'll also notice we lost some intensity. If it's displaced low, meaning that it's pressed down into the sample holder, the peak shifted to lower 2 theta, and also we lost some intensity. How much of a displacement are we talking about here? This was a displacement of approximately 300 microns. It's not a lot of displacement, of 0.3 millimeters, and you'll see it has a dramatic effect on the peak position. Now, if you're working with a powder sample, you could include some type of internal standard that you know where the peak should be, and that could correct for some shifting if you have sample displacement. However, it doesn't correct for the loss of intensity. So if you need quantitative qualitative results, sample displacement can affect your quantitative analysis. So positioning the sample in the proper position is important for good peak position and peak intensity. So something that you probably should consider doing in your laboratory is some kind of a specimen preparation reproducibility study. Here we had 4 groups that were asked to prepare a powder sample that was a 50-50 mix of potassium chloride and aluminum oxide. You could use any common type material, and the 4 groups were given the sample and said, prepare this in the front pack sample holder. And we focused on the potassium chloride 200 peak, 4 groups with the same sample. And you'll see that when I look at that KCl peak, there is a distribution of 2 theta positions in the observed data. You'll see that the peak position expected using copper radiation is 28.345 degrees 2 theta, and one group was very close to having it in the correct spot. Everybody else, you'll see a shift to higher angle, which means that in our well of our sample, they were displaced high. In addition to being displaced high, we see the shift in the peak position, but we also saw a loss in peak intensity. So what does this mean when you go to do phase ID? Well, the mean for this group was 28.422 degrees. And this peak right here is probably a big factor for that shift. The plus or minus was 0.11 degrees. If I look at what's that mean from a despacing point of view, that means I have plus or minus 0.012 angstrom range. And if I go to the PDF5 plus database and I say, how many peaks have this peak position, despacing, plus or minus 0.012 angstroms, there's 6,929 entries. If you're trying to do phase ID, you're making it more difficult to get the correct answer because of your peak shift. On the other hand, if I said I was in the correct peak position and I had no error in my despacing, there are only 25 entries that meet that criteria, and it certainly simplifies your phase identification. When you look at your diffractometer software, a couple things to pay attention to. All of the phase identification programs from your different diffractometer companies and from the ICDD, Sieve, and Jade software, they will have some kind of what they call a 2 theta window, a search window, a delta 2 theta. This is that plus or minus that they're giving you a cushion because they understand there's a high probability you'll have some kind of an error in your data. And the bigger you make this error, the chances are you'll get a hit. But if you make this window too big, you may have too many hits. So you want to be careful what you make your 2 theta window for your searching. In addition, they're going to have some kind of goodness of match or figure of merit. If it's a figure of merit, FOM, some software says that the smaller the value, the better the hit. Some will say the larger the value, the better the hit. Some using goodness of match. In this case here with the ICDD Sieve, it looks at 8 peaks. And if you had a perfect match, your score would be 8,000. And then as the score drops, you have some delta 2 theta in your peak position versus the expected peak position. All of these are very good. They're usable. What you want to understand is for your software, what is the delta 2 theta being used? And typically it can be adjusted. If you make it smaller, that means you think you have really good data. If you make it larger, maybe your data has some errors in it, but you're also allowing more phases to be in the hits. And then also understand what your figure of merit is doing for your software. These are common powder sample holders. We've been focusing right now on the front loading holder. This is the one that's primarily provided by most of your instrument manufacturers. Some of them will also provide what we call a backloading holder. And in this case, there's actually a hole drilled all the way through your holder itself. You put the holder, the front side, on a flat surface like a piece of glass. You put the powder in, we call it from the back. You then have maybe some kind of a plug that goes in there to go behind the sample. Turn it around, remove the glass, and you have a pretty good sense that it's going to be flat and level with the surface of your sample holder. There's also something called a side loading or side drifting, where you actually put the sample, in this case in a little jig, has a little funnel here that helps to feed the sample through the side. And then this rests against a piece of glass here. This also will give you a sample that pretty much should be flat and level with the sample holder itself. This side loading also can help sometimes when you have some asymmetric particles, with a little bit of reduction in preferred orientation. So why do people use the front loading when the chances are that you'll get a little bit of sample displacement error? This is the fastest method for preparing your sample. The side loading is the slowest method, and so people tend to get a little bit of a hurry. They use the front loading. It will work. You just have to be careful. Everything, though, is not a powder. And you have to accept the fact that sometimes you're going to have some other issues come into play. Here is a coating of nickel phosphide, about 100 microns, on a steel roller. And we were asked to take a look at it, but we can't cut it and we can't grind it up. So in this particular situation, what do? We made a little lab jack and jig to push the sample. And in this instrument here, there is a reference flat that a flat sample would typically go against. So in our case here with this, what we did was we pushed the sample up till part of it was resting against the flat. And then we use a smaller divergence slit. So we're only looking at a small region here on the sample, with the understanding it's not going to be perfect, but allow us to do the particular study, which was, when does it crystallize? So in this case, we could take the roller, we could heat the spot that we needed to see, different temperatures, and determine that the crystallization temperature and enough information was there, we could identify the phase, understanding that it wasn't a perfect diffraction peak, but sometimes that's what you have to do when you have real samples. Okay, we're going to shift now to counting statistics. In counting statistics, basically your variation in intensity is a function of the square root of counts. So if I have an intensity of 100 counts, that's plus or minus 10. So I have what we call 10% counting statistics. If I have 1,000, it's 33.3%. If I had 10,000 counts, it's 1% counting statistics. Now, in an ideal world, everything would have 1% counting statistics, which means your signal to noise would be fabulous. However, the time to collect data like that can be prohibitive. So here's just an example of the lanthanum hexaboride peak. It's the 422 peak at around 130 degrees to theta. And we can see with normalized intensity, a comparison of collecting with 0.1 second per step and collecting 10 seconds per step. The red pattern, 1 second per step, you'll get the indication here that it's a very noisy pattern because the counting statistics are low. When I count at 10 seconds per step, so now I'm really counting 100 times longer than the 0.1 second per step. The pattern, which is the black curve here, is very smooth. and you really see very little variation, statistical noise. So this is really what the counting statistics will do for you. Even though the general peak shape is similar, if you try to put this through some kind of automated peak searching, though, because they use either some kind of first or second derivative algorithm, it will have some problems where you get some of these spikes in here in terms of getting accurate peak determination. So just an example where this comes into play, here's a pharmaceutical pill. It's a generic clopidogrel bisulfate, a generic for Plavix, used for treatment of people who have had heart attacks or strokes and reduce platelet aggregation. Grind it up into a fine powder, and you'll have instruments, particularly strip detectors, where you'll be demonstrating and showing that you can run a pattern of gold in about 30 seconds and identify the gold. And yes, that's true, because first of all, gold is a great scatter of X-rays. Second, it's a single phase sample, so you're going to get that as an answer. But what do you do when it's more of a composite complex sample? So here are scans of this powder sample run at 33, 167, 28 minutes, and 4.5 hour scans. Now I've increased the intensity because the 33 is obviously going to be 33 seconds going to be much lower counts than 4.6 hours. So we've normalized the intensity, and then we've done a shift just so we can differentiate the peaks. If I say, can I do phase ID on these samples? Well, in the top 3 scans, I could identify the major phase, the clopidogrel bisulfate. However, the question being asked was, can I identify everything in the sample? And that's when you really have to rely on a long scan. So here's a comparison of the scan that was at 4.6 hours, the scan that was at 33 seconds. And what you'll see is that at 4.6 hours, I can start to see some of the details in the diffraction pattern. And at 33 seconds, if I tried to do a peak searching, it would be putting multiple peaks in here, not because there are multiple peaks, but because the pattern just has poor counting statistics. What is the background? Well, at 33 seconds, the background is 4 counts on average. So that means I have 4 plus or minus 2, and that's 50% counting statistics. At 2,000 counts, now my counting statistics are about 2.2%, and I'm able to get more detail. The net result is, with that long, detailed data collection scan, I'm able to identify all of the phases, including amorphous components, in this sample. You would not be able to do that with the other scans. So it brings up the question, do I need to collect everything of a 4 or 5, 6 hour scan? And the problem is, you can't. This is a week of data samples in an industrial XRD laboratory, and there's no way you can collect every scan at 4 or 5 hours per sample. And so this is where you have to use judgment. What is it you're trying to do? If you need the kind of detail we needed on that pharmaceutical pill, then yes, you're going to need a very, very long scan. But if you need a cursory phase identification, scans that probably are in the range of 15 to 30 minutes probably will answer the question you're looking for. So you need to understand what's the problem trying to be solved and what is the time available in your laboratory to work with this. This is the case where instruments that have sample changers that can run through the night are very beneficial, particularly in labs that get the type of samples you see here in this slide. Let's talk next about your step size. What's the appropriate step size when I'm collecting my data? So here's our lanthanum hexaboride peak again, and collected the data, 3 different step sizes, 0.1 degree, 0.02 degree, and 0.005 degree. Now, in a conventional powder diffractometer, the 0.005 is probably too small. At a synchrotron, 0.001 is actually appropriate. So you have to think about, am I in my lab or a sample at a synchrotron. If I separate the peaks just so that we can see the difference in the patterns here, what we find is that at 0.1 degree, I'm really missing some of the peak profile. And this is because the step size is too big. At 0.005, I'm getting good peak profile, but I've got so many data points, it's not really giving me any additional information. And so it's probably a little bit too small. And in this particular case, the 0.02 degree step size is adequate to give us the peak position and the peak profile. As a general guideline, you'd like to have at least 5 data points above the peak full width at half maximum. So if I look at my peak and I find the half height and I look at that peak width, 5 points at least above that is a good guideline. If you have a little bit more, that's fine. If you have less, you're not going to get the full peak profile. Here's just an example here, polyethylene glycol. Low molecular weight is the blue pattern and it's amorphous. High molecular weight's the red pattern, it's semicrystalline. So for small crystallites, amorphous materials, a step size of 0.05 to 0.1 would be adequate in this case. For the larger crystallite size material, typically 0.01 to 0.02 is probably adequate to get the peak profile you need to see, as well as get the good background that you're looking for. Let's move into some things about particles. And remember in the beginning, we talked about single crystal Lowry spots versus Debye rings for powders. One of the things strip detectors can do is they can record partial Debye rings, kind of like the old Debye and Scherrer film cameras. And here's an example of finer particles to coarse particles. And the finer particles, you begin to see a more complete Debye ring, but as the coarse particle becomes more coarse, it becomes almost single crystal-like, and you start seeing Lowry spots. And so if my diffractometer is collecting the data, and I only have a few diffraction spots, my particle statistics are not good, which means my intensities will be errant compared to what we should see in a random powder. So let's quickly talk about particle size versus crystallite size. When we talk about particles, and they could be individual crystals, and in this case, the particle size is equal to the crystallite size, almost like having small little single crystals. But particles are more often imperfect, and they can have things like dislocations, twin walls, grain boundaries, stacking faults within the particle itself. And when this is the case, the particle size is larger than the crystallite size. And this is typically the case. So what we think about here is that when we look at an individual crystallite, we're thinking of something that has a repeating lattice. Typically, it's a 3D component, and it's cut off or truncated by these different boundaries, such as the dislocations, grain boundaries, etc., within the particle itself. So when optical microscopy looks at a particle and says, oh, these are 5 micron, 100 micron, 50 micron particles, but X-ray diffraction says, oh, the crystallite size is 1,000 angstroms. That's because within that particle, there are some kind of perturbation of the lattice. So just an example what that does to your diffraction pattern. If you have large crystallites or larger crystallites, your diffraction peaks tend to be narrow. If you have very small crystallites or nanoparticles, your diffraction peaks tend to be broad. And XRD is very good at looking at things like this crystallite size, nominally up to around 1,000 angstroms. As you get beyond 1,000 angstroms, the peak width starts to get so narrow that most of the broadening is due to instrument artifacts rather than the sample itself. So what is needed for powder XRD analysis? We want small particles because we want lots of individual crystalline diffraction events. We can use something like a sieve to sort of separate out particle size, but remember XRD is measuring the crystallite size. You can have different sieves, and the sieve will have what's called a mesh size. It's really how many, I'll call it wire pairs per inch, and depending upon the number of pairs will affect the hole opening in the mesh screen, and that will influence what particles will pass through. Okay. Now, the number of spherical particles in an irradiated volume. If you had 40 micron particles, and let's say your sample well was a 20 millimeter cube, basically opening there, or let's say a cylinder, you would have about 597,000 particles. Take in contrast, if you had 1 micron particles, that would equate to 38 billion particles that are there. And so you have a better chance of getting a true randomization of your sample. How do I make small particles, or what do I need to do to grind my sample? And these are some common grinding tools. The traditional is just a hand grinder with a mortar and pestle, typically made of alumina or agate. You have what we call an impact mortar and pestle. This is what you use oftentimes if you've received sort of a large, say like a rock sample, and you use this to crush that into smaller, let's say, component that then is ground to a fine powder. And then there are mechanical grinders, such as this mechanical mill, that you put some particles inside a tube, and then you have beads of tungsten carbide, steel, zirconia agate, even polycarbonate that would then grind the sample down to some kind of fine size. Sieves can be used to sort of segregate out large and small particles. You can buy what are called ASTM certified sieves. Generally, for your powder XRD work, it doesn't have to be ASTM certified, but you want to get a good, reliable sieve. Now, the problem here is these metal sieves are very durable. And by the way, you would want to get those made out of stainless steel. They do make them out of brass. The problem with those is that if they get washed and the water isn't dried away properly, you'll get corrosion of the brass. It'll sort of make copper oxides, which will then give you sort of some contamination. So stainless steel is best. There's a problem, though, with any of these metal sieves. Particles can and do get trapped in the mesh, and they can be difficult to clean. So if this is a concern for you, there are sieve polymer cloths. Typically, they're made of nylon or polyester. You can buy a large roll, or you can buy pre-cut pieces. This polymer cloth will fit inside a plastic rings, and you can use this to sieve your material. Now, these are not ASTM certified, but they are very good for being able to sieve, segregate out large, small particles. And when you're done with that sieve material, it can then be disposed of in your chemical waste, as opposed to reusing it and contaminating it with the next sample. Now, a classic study by Klug and Alexander showed the effect of particle size on your intensity variation. In this particular case, they looked at different fractions of quartz, and they focused on a particular quartz peak. And when they looked at this, they said that if you had a 15 to 50 micron range of particles, your reproducibility and your intensity, your deviation was 18%. When you had 5 micron or smaller particle distribution, your reproducibility, your standard deviation was 1.2%. So the smaller your particles and the finer your distribution, the better your reproducibility will be in your intensities. So that experiment I showed earlier where we took a KCl aluminum oxide mix and had people take a look at that, that's something else you could do in your laboratory with a mixture to see what's the reproducibility of my peak intensities if I wanted to do quantitative analysis. Particle shapes can cause problem. Don't assume you have spherical. In fact, you almost always won't have spherical particles, but you can sort of have what we would call uniform size, referred to as equant. You can have tabular, blades, acicular, and what happens when you get some of these asymmetric particles, they will tend to align parallel when you're packing it in your sample holder, and this will give you what we call preferred orientation. Now, preferred orientation doesn't mean it's what you prefer, it means what the particle does. Maybe a better term is preferential orientation, but this preferred orientation is the common term that's used, and we try to eliminate that. Here's just some examples of different particle morphologies of different materials, and you can see you have anything from a sort of a fibrous type, plates, you have sort of needle shards, even little different kind of platelets here. So you have to be aware that sometimes you have to try to remove this morphology effect to get a random powder pattern. So just a couple of cases of look at here, preferred orientation. So here is a piece of lepidolite, which is a hot item in the energy market because this is a lithium containing mica type sample. If I look at a sheet of this material and I put it in the diffractometer, well, that sheet is going to lie parallel to my sample surface, and it's a lot of oriented OOL lattice planes all parallel to each other. And so when you run the diffraction pattern, you see the 1, 2, 3, 4, 5 diffraction peaks. This is evidence of preferred orientation. Now you can use something called a Macron mill, and when you use this mill, you have some of your material is put in a cup with a milling media. These are cylinders of, could be agate, alumina, zirconia. You add a little solvent, you cap it up, and then it vibrates, it shakes it back and forth, and you do this for a period of time to try to micronize your sample. If you take this particular mica type sample and you milled it for 3 minutes, well, it turns out I have a diffraction pattern that looks almost the same. How come? Essentially what I did with the 3-minute mill on this particular sample is I just made smaller plates. And these smaller plates, when packed in a sample holder, still lie flat. I see preferred orientation. I went to an extreme and did a 23-minute mill. That's pretty long for one of these types of sample preparations. But you can see now I have a more random orientation within my sample because I have a more random orientation and broken up these plates. So this is really going from preferred orientation to a more randomly oriented sample. Now, sometimes you want to see the preferred orientation. You want to know what that orientation is, but if you need to do phase ID or quantitative analysis, it's better if you can randomize the sample. Another effect is called low sampling statistics. Here's a case of needles, gold needles on a quartz matrix, and these needles turned out are rutile TiO2. If I take a few needles and put them onto a zero background holder, I get some diffraction peaks, but it's not a consistent story. I see a 110, 220, but I also see a 200, 400, and I even see a 310. There's really no logic to any kind of preferred orientation. It's just a few peaks. On the other hand, if I grind a few of those needles into a powder and put that on a zero background plate, I get a random diffraction pattern that allows me to easily identify that this is in fact rutile TiO2. So preferred orientation, you tend to have the same family of planes for multiple peaks. For low sampling statistics, you kind of have, you don't hit your random powder pattern, and you seem to have some arbitrary diffraction peaks showing up. That means you need better sampling statistics. So to summarize with the sample, your experimental goals, specimen parameters, ideal if you want a good D-spacings, We're going to want a thin sample. Particle size can be on the order of, say, 20 to 40 microns. No sample displacement, so you have very little transparency error, well-resolved peaks, good for phase ID and unit cell determination. If you want good intensities, you would have a thicker sample, but to have reproducible intensities, the particle size, you'd like to have it less than 5 micron. Now, here's a reality check. It is very, very difficult to get 5 micron particles. Highly likely you won't get there unless you do extensive grinding on your sample. Avoids preferred orientation. You get nice smooth profiles, good for quantitative analysis and structure analysis. So let's say we've done all of this. We've got the perfect sample prepared. Then you're ready to do your phase ID. So here's an example of a well-prepared sample. It's a mixture, and you can use automated analysis, such as, an example, our JADE one-click analysis, where you immediately were able to identify the phases. It did your Rietveld refinement. It did your quantitative analysis of the phases that were present, rutile TiO2, anatase TiO2, and hematite iron oxide. You have information in the PDF5 database that tells you the structure of these phases, and you can investigate further any of these structures because you can look at, for example, the phase identification of your material. Okay, so with that, apologies here. Apologies, I hit the wrong button. So let me just say that for this, this is the ICDD team. These are the folks that make everything happen. We have our group in Pennsylvania, a member in South Carolina, our California group, our China representative, and our new representative in Italy. So thanks to them for everything that you see from ICDD. And with that, I'll say thank you.
Visit ICDD.com to register for upcoming webinars and to watch previous ones.